Hello everyone. I want to quickly follow up on my previous session on how transformer work. All right, look at this paper. This is the original attention is all you need paper. So it has this attention visualization. Specifically, it mentioned about calculating attention against individual token. For each token, you need to calculate this attention score against all other tokens. Let me say it again. Individual token will need to calculate the attention against all other tokens in the sequence. Okay, if you think about it, this in a programming language point of view, this can be implemented in a nested for loop, like 2 layers of for loop. All right. As a result, the complexity for this calculation is quadratic, right? As I also mentioned over here, the self-attention for the complexity per layer is big O of n squared multiplied d. N is a sequence and d is a representation dimension. All right, d is pretty much the embedding dimension. In the GPT-2 code base, this is a sequence. This is a 1024, and embedding dimension is 768. All right, let's look at the code just over here. And the attention calculation, this one, we don't see a nested for loop. What we see is simply this matrix multiplication. One line of the statement will just implement this attention calculation, which is a good news because essentially the whole sequence can run in parallel. All right, which is very good, especially on a GPU friendly environment. When they do this linear algebra computation, can run everything in parallel. All right, this is also mentioned in another paper we talked about before in the inference challenges. It talks about this quadratic complexity attention operation, which is something we should pay attention to. Okay, that's this part. All right, let's quickly switch to the notebook. Okay, in the notebook, we previously talk about the how to use it in general, especially using the high level way of doing this, using a pipeline. Mentioned about here, high level helper in a pipeline. However, they also mentioned you can also load the model directly in your code base. Okay, let's also cover this bit. We can see this one. This one. We can just do this directly. Load the tokenizer, load the model. Okay. Let me also comment this. If we run this, it will also give you all the model config files. All right. What does this do? You can see some of the hyperparameters like the context length, embedding dimension, how many headers, and how many layers, and so on and so forth. Some of them you can change. Some of them it's not recommended to change. Also, this vocabulary size for GPT-2 is 50K, around 50K. All right. Once we get the tokenizer model, we can start using it. Right. One way to use it is simply convert it, tokenizer, return as the tensor format, and then give you all the input. Right. This is the tokenized result for individual input. All right. What we can do is if we want to go that layer by layer, okay, what we can do is we feed the whole input into the model, and then we can get the output. All right. Specifically, this output has something called logits. Okay. What does the logit stands for? These logits are just the raw, unnormalized output values before we ever applying the softmax to get the probability. Okay, this is the raw output. Okay, we also see the shape. The shape is batch size, sequence length, and vocabulary size. Okay, we have one sequence. This is one sequence. This is one sentence, which is the batch size is 1. The sequence length is this. Is how many tokens? That's 5, and then vocabulary size is around 50K. All right, and then we can get the final piece and then run this prediction. Okay, I didn't input the torch. Okay, let me quickly do it over here. All right, we can find the index of of the token with the highest logic value, we can get the predicted token over here. Okay, so we can get the value is floor. You see the prefix, you have a space. Okay, this is how you get this next token. Okay, it means a cat sat on the floor. Another way you can do this, if you want to look at the all the distribution and the probability value, you can also find the top k. In this case, I find the top 10 and also print out their probability. All right, you can see floor is the top one, and then you see edge ground. Looks like all of them are making sense in the context of this sentence. Okay, that's what you can do. However, you don't have to go through this get the logics and then compute the output. You can just directly do this all together in one place. Okay, you can just get the input and then get the output with this generate method, and then this output ID you can decode it straight away, and then you can get the decoded text. All right. One thing I do want to mention is we used to see this warning. It's talk about the padding ID is set to this end of sequence token ID for open-ended generation. This is because when GPT was trained, it was not trained with a padding. So as a result, what you can do to suppress that warning is simply to provide this pad token ID equals to this end of sequence token ID. It will just suppress the warning. All right, and once you get it, and then you can get the output. This is just different ways you can generate the output, either using this high-level pipeline, or you can use it directly. You can also see what's inside behind this pipeline. You get all the process through the tokenization. You get the input token IDs, and then you get the output IDs. All right. The next part, what I plan to do is going to use this transformers to help us go through layer by layer to look at how transformers work. All right. Like we mentioned before, we have this one. It has multiple layers. If we're adding this embedding layer, that's like 12 layers for transformers and one embedding, that's 13 layers. We will see this from input to output and the transformers. All right. Before we even start, let's quickly go back to this logics. Okay, so this logics, where does this located? Okay, this is located at this one. This is just after the output of the transformer, and then do a linear projection. This is the logic output, and then you do the softmax and you get the probability. Okay, so the logics output is over here. All right. And then we will very soon see the output at this stage, and the this transformer output, which is normally is referred as this hidden states. All right, let's quickly look at this one. So let's quickly import everything. Okay, tokenizer, and then we have specified this token ID, pad token ID, and then we are going to evaluate these two sentences. So one is he went to the bank to deposit money. The second is she sat on the bank of the river. As you can imagine, I will going to evaluate this representation, embedding representation for this bank and this bank, right? If we just tokenize the value, we can see over here. Okay, two sentences and tokenized value. Both this bank have the same output for a static mapping, 3331. What we want to see is gradually, okay, this representation will change, okay, because semantically, this bank and this bank refer to two different things, okay. And next thing is, like we did before, do the tokenization, and then we get the input ID. This one is a bank, this one is a bank. This time, we are going to specify this something called output token states equals true. Okay, in this case, we can get all the so-called hidden states. Individual hidden states just refers to individual layers of the output in the transformer architecture. Okay, like I mentioned before, there are 12 transformers and also one embedding layer. So This hidden states, we can see the size of the hidden states will be 13, including the input embedding. And then at the individual layer, okay, it will be this batch size, sequence length, and also the feature dimensions. These feature dimensions will just be the same as this value, okay, embedding dimension. Okay, where does the source code? In the source code refers to these shapes. Okay, we can quickly check both the shape for this hidden state individual layer. It should be located over. It should be over here, right? This is the batch size. This is sequence size. This is the features dimension. Okay, this is when they calculate this attention. This is the size. Okay, another size we can refer to is at the end the logic output. Okay, at the logic output you see you see the shape is batch size, sequence size, and the vocabulary size. Okay, this refers to logic output. So let's quickly go back. We know that we have 13 layers, and then per layer you have this shape. Okay, next time we can evaluate the bank position, which is the index equals 4 at the fifth token. What we plan to do is using two things. So one is to measure the similarity between this embedding representation. Another thing we are going to calculate is this something called L2 distance. Okay, to consider this embedding, after the embedding, individual token or individual word is mapped to a high dimensional vector space. Vector space, okay, like this one is a two-dimensional, but in the case of GPT-2, that's 768 dimensions by a very high dimensional space. Because higher dimension basically means you get to have deeper and richer meanings for each token or each word. All right, and then we get the similarity calculation and distance calculation. Similarity, we are doing this cosine similarity. Just measure in the vector space. How does this the angle between these two vectors, right? It ranges from -1 to 1, right? If it's 1, means two vectors are point to the same direction. -1 means opposite direction, and 0 means they are like unrelated, orthogonal, basically, right? They are kind of orthogonal and unrelated. And L2 distance, it just measures the distance between two vectors in this space. 0 means they are identical. Smaller means they close to each other, and larger means two vectors are further apart. All right. Let's yeah, and you probably hear this vector and this embedding a lot when it comes to the context of retrieval augmented generation. You're definitely gonna see lots of index to the embedding, and then save that into the vector database, and then do a retrieval to a semantic search. All right, this is pretty much similar to what it happens in this GPT-2 model. So what we can do is we can run this. We will see, okay, at each layer, how does these two banks, okay, their similarity and distance. We can see very clearly. At the beginning, layer 0, that's the embedding layer. They are identical in both similarity and distance. And gradually, we see the similarity decrease, and also the distance increase. But at the final layer, it kind of slightly increase and they slightly decrease. All right, which is a very interesting pattern, especially in the final layer, right? It just shows that multiple layers of transformers, how do they comprehend the overall input sequence? Okay, so we can pretty much see in the early layers the model processing local context. Okay, and then they do this incorporate information from neighboring words. And the middle layers, the model can distinguish between this bank, which is a financial institution, the other bank, which is a river bank. As a result, the similarity and distance just getting further. And then the final layer, because similarity will increase slightly because the model is preparing the representations for the next token prediction. So because we do see some similarity between these two sentences, because both of them are noun follow the, so they share some similarity in linguistic patterns and also grammatical patterns from this language modeling point of view. Okay, feel free to run this code, see this pattern, and thanks for watching.